Numerical Series 3. A gas is heated in a duct as it flows over a resistance heater. Consider a 101 kilowatt electric heating system. The gas enters the heating section of the duct at 100 kilopascal and 27 degrees Celsius with a volume flow rate of 15 meter cube per second. If heat is lost from the gas in the duct to the surroundings at a rate of 51 kilowatt, the exit temperature of the gas is: assume constant pressure, ideal gas, negligible change in kinetic and potential energies, and constant specific heat. Cp equal to 1 kilojoule per kg Kelvin, R equal to 0.5 kilojoule per kg Kelvin. So the given options are 32 degrees Celsius, 37 degrees Celsius, 76 degrees Celsius and 53 degrees Celsius. So after calculation, we will see which one is the right option for the given question. So before we start solving the problem, let's briefly discuss the approach we will be using. So first, let's draw a duct as per the question. So this is a duct. With this duct, an electric heater is attached for the heating purpose of the gas. So the gas enters to this duct from this section known as inlet section, and the gas after heating leaves the duct from this section known as exit section. So see, the mass which is entering from this side, the same mass leaves the duct from this side. So here we can say that the rate of mass flow is constant. As here we see the rate of mass flow is constant, it means we can say that it is a case of steady flow. So now we see what are the data given in this question. So the first data given is 101 kilowatt. So see, consider a 101 kilowatt electric heating system. This 101 kilowatt seems like a heat transfer, but actually this 101 kilowatt is a work transfer. If you refer the chapter Heat and Work Transfer of any standard thermodynamics book, you will find some typical work form other than PDV work, like electrical work, shaft work, paddle wheel work. So this 101 kilowatt here seems to be electrical work. Now what is this electrical work? When an electric current flows through a resistor, or you can say a system, there is a work transfer to the system. So that work transfer is nothing but electrical work. So here we can see this 101 kilowatt can be considered as W equal to 101 kilowatt. So here, as we discuss the definition of the electrical work, that is the work transfer to the system, it means we can say that the work done on the system. So it means here we can use the minus sign for this work or for this magnitude, that is 101 kilowatt. So here we can say that this is minus 101 kilowatt. Next data we will see here, the gas enters the heating section of the duct at 100 kilopascal, 27 degrees Celsius and volume flow rate of 15 meter cube per second. So these are the properties of the gas at inlet section. So the properties like pressure P1 at inlet section is equal to 100 kilopascal. Temperature at inlet section is to be T1, that is equal to 27 degrees Celsius. Let's convert this into Kelvin, that is equal to 300 Kelvin. Next we consider the volume flow rate at inlet section to be V1 dot is equal to 15 meter cube per second. Next data we will see here. If heat is lost from the gas in the duct to the surrounding at a rate of 51 kilowatt, it means here it is mentioned that heat rejection to the surrounding from the system, that is Q. So it is mentioned that Q equal to minus 51 kilowatt, as this 51 kilowatt is the heat rejection. So that's why here we consider minus sign. Next data we will see here, that is Cp equal to 1 kilojoule per kg Kelvin. Next data is R equal to 0.5 kilojoule per kg Kelvin. Next, we will see what we have to calculate for this question. See, it is mentioned that the exit temperature of the gas. So this exit temperature of the gas, it means here we have to find out the temperature with which the gas leaves this duct. So here the temperature it is considered to be T2. So this T2 we have to find out for this question. So now the question arises that which principle we are going to use here, or what formula we are going to use here. So as we discussed earlier that this is a case of steady flow, so here we are going to use the steady flow energy equation. And we are going to use steady flow energy equation with respect to time. So why time we consider with respect to time? Because see, here work done is given in kilowatt and heat transfer is given in kilowatt and volume flow rate is given, that is meter cube per second. It means it is with respect to time it is given. So here as it is mentioned in the data that is with respect to time, here we consider the steady flow energy equation to be m dot h1 plus v1 square by 2 plus z1g plus q equal to m dot h2 plus v2 square by 2 plus z2g plus w. So this is the steady flow energy equation with respect to time. But in the question it is mentioned that this is a case of an ideal gas as well as there is negligible change in kinetic and potential energies. So simply here we neglect the kinetic and potential energies from both the sides of the steady flow energy equation. So after neglecting this, we consider the equation is reduced to m dot h1 plus q equal to m dot h2 plus w. So now we see in this equation we have the magnitude of q and w, but we don't have the magnitude of m dot h1 and h2. So here we know that the ideal gas, this is the condition it is given for the question. It means the gas is assumed to be ideal gas. So as gas is considered to be ideal gas, so here we use the relation PV equal to MRT. So if we consider this equation for inlet section, so here we consider P1, V1, that is mass is constant, so we consider this M. as inlet mass R and T1. And here we consider the rate of mass flow. So that's why we consider m dot. As we consider the rate of mass flow to the right hand side, so here we consider the rate of volume flow. So here we consider this is V1 dot. So see, we have P1 value, V1 dot value, T1, R value is also given. So after substituting the magnitude here, we get the magnitude of m dot. So let's solve this. So P1 is 100 into V1 dot is 15 is equal to m dot into R is 0.5 into T1. Sorry, T1 is given, that is 300 Kelvin. So after solving this one, we get m dot is equal to 10 kg per second. So this is the magnitude of m dot which we are going to use in the steady flow energy equation. So next we have to calculate H1. So we know that H equal to CPT. So it means if we consider H1, so it becomes CPT1. So here we consider H1 is equal to Cp is what? That is given 1 into T1 is 300. So here we consider this H1 is equal to 300 kilojoule per kg. So this is the magnitude of H1. So next we will see H2. So H2 equal to CpT2. So as H equal to CpT2, so H2 equal to Cp is 1 into T2 is what? That is the thing which we have to calculate for this question. So keep this equation as it is, H2 equal to T2. So this also we are going to use in this steady flow energy equation. Now let us consider the steady flow energy equation again, that is m dot H1 plus Q equal to m dot H2 plus W. So that imply in place of m dot we substitute 10 into H1 as 300 plus Q as minus 51 equal to m dot again 10 into H2 as T2 plus W as minus 101. So next we see after solving this expression, we will consider T2 as 305 Kelvin. But in the question, the options are given in degree Celsius. So let's convert this T2 from Kelvin to degree Celsius. So we consider T2 is equal to 305 minus 273. So that implies T2 is equal to 32 degrees Celsius. So this is the final answer for the given question. So here it is clearly visible that option A is the right answer for the given question. Thanks for watching and see you in the next video.